Imagine a signal so powerful it crosses billions of light years in the blink of an eye, only to vanish without a trace. These are fast radio bursts, some of the most baffling phenomena in the cosmos. In just milliseconds, they release as much energy as the sun does in days, weeks, even years. And here's the thing, we still don't know what creates them. Picture this, a burst detected in 2020, originating from a galaxy so distant, its light began traveling when the universe was just half its current age. By the time it reached us, the signal lasted less time than it takes to snap your fingers. Yet in that fleeting instant, it left astronomers with more questions than answers. Fast radio bursts, or FRB, are like cosmic whispers from the far reaches of space. They arrive unannounced, crackling through the void, and then disappear before we can fully grasp their meaning. Some repeat in erratic patterns, while others are one-off events never heard from again. The strangest part, we've traced some to magnetars, the ultra-dense, spinning corpses of dead stars, but others come from places with no obvious source at all. It's as if the universe is playing a game of hide and seek, leaving behind clues that defy explanation. Could these bursts be the aftermath of collapsing black holes? The echoes of ancient cosmic collisions, or something even more extraordinary beyond our current understanding? That's where the mystery deepens. Over the years, astronomers have catalogued dozens of these enigmatic signals, each one peeling back another layer of intrigue. In this journey, we'll uncover 30 of the most compelling puzzles surrounding FRBs, from their mind-bending origins to the bizarre patterns that hint at intelligence, though we're not jumping to conclusions just yet. We'll explore how these bursts warp space-time itself, how they might be mapping the unseen matter between galaxies, and why some scientists believe they could revolutionize our understanding of the universe. So buckle up. What follows isn't just a story about distant radio waves, it's a detective story written in the fabric of the cosmos, and you're about to become part of the investigation. It all started in 2007, when astronomer Duncan Lorimer and his student David Narkevic were sifting through old data from the Parkes radio telescope in Australia. Buried in the static was something no one expected: a single, blazing burst of radio waves lasting just 5 milliseconds. At first, they thought it might be a glitch, some earthly interference masquerading as a cosmic signal. After all, telescopes pick up all sorts of noise, from passing satellites to microwave ovens left running in nearby buildings, but this was different. This burst had traveled an unfathomable distance, its signal stretched by the expansion of the universe itself. It became known as the Lorimer Burst, and it sent shockwaves through the astronomy community. Skeptics argued it could be anything: a fluke, an instrument error, even a previously unknown type of stellar explosion. But then, something extraordinary happened. Over the next few years, more bursts trickled in. Each one matched the same bizarre profile: an incredibly bright flash of radio waves vanishing almost as soon as it appeared. By 2013, there was no denying it: FRBs were real, and they were coming from deep space. The scientific community went from doubt to fascination almost overnight. Suddenly, astronomers were racing to explain what could produce such intense, fleeting energy. What made the Lorimer Burst so confounding wasn't just its power or its distance. It was the way it defied all expectations. Nothing in our known universe should be able to generate that much energy in such a short time, at least nothing we understood back then. Some theorists scrambled to pin it on known cosmic objects, like neutron stars colliding or black holes swallowing matter. Others dared to suggest more exotic possibilities, like cosmic strings vibrating through space-time, or even, though cautiously, technological signatures from distant civilizations. The debate raged on, but one thing became clear: FRBs weren't just a curiosity. They were a window into the universe's most extreme and unexplained phenomena. And this was just the beginning. The discovery of repeating FRBs in 2016 turned everything on its head. If some bursts repeated while others didn't, what did that say about their origins? Were there multiple cosmic engines powering these signals, each with its own rules? The Lorimer Burst had opened a door, one that led to a labyrinth of cosmic mysteries we're still navigating today. The discovery of repeating fast radio bursts shattered the assumption that all these cosmic signals were one-time events. Take FRB 121102, the first known repeater detected in 2016. Unlike the Lorimer Burst, which flashed once and never returned, this source kept sending out bursts in unpredictable patterns, sometimes days or even months apart. Imagine tuning a radio to static, only to catch the same mysterious voice breaking through at random intervals, never following a schedule. That's what astronomers faced, and it upended every existing theory. The difference between repeaters and one-off bursts isn't just about timing. Repeaters like FRB 121102 tend to have lower energy compared to the colossal, single blasts that vanish without a trace. It's like comparing a campfire that flickers sporadically to a firework that explodes once with blinding intensity. Even more intriguing, repeaters often originate from dense, turbulent regions of star formation, while one-offs have been traced to quieter corners of their host galaxies. This split hints at two entirely different cosmic engines powering these phenomena. So why the divide? One leading theory suggests repeaters come from magnetars, highly magnetized neutron stars with crusts that occasionally crack under immense strain, releasing bursts of energy. These stars could have just enough stability to produce multiple flares over time. But one-off bursts, they might be the final, catastrophic screams of objects being destroyed, neutron stars colliding, black holes swallowing matter, or even hypothetical cosmic strings snapping. The challenge is that we've never caught a one-off burst in the act of creation, leaving us to piece together clues from their aftermath. The real head-scratcher is FRB 121102's home, a dwarf galaxy 3 billion light-years away, brimming with young stars and chaos. This environment suggests a link to extreme stellar activity, but here's the twist: not all repeaters come from such turbulent nurseries. Some emerge from older galaxies, muddying the waters further. It's as if the universe is telling us there's no single rulebook for FRBs. Then there's the enigma of periodicity. A handful of repeating bursts like FRB 180916 fire off in cycles, active for days, then silent for weeks. This rhythmic behavior points to something orbiting another object, its bursts flaring when conditions align just right. Could it be a neutron star wobbling around a companion star or black hole? Or is there some other celestial clockwork at play? Each new repeater we find adds another layer to the puzzle, proving these aren't random accidents, they're following rules we haven't decoded yet. The dichotomy between repeaters and one-offs forces us to confront a humbling truth. FRBs might not be one mystery, but many. Some could be stellar tantrums, others cosmic catastrophes, and a few, well, they might belong to categories we haven't even imagined. The more we learn, the clearer it becomes. Fast radio bursts aren't just signals. They're a mirror held up to the universe's most violent, mysterious corners, reflecting back questions we're only beginning to ask. One of the most astonishing truths about fast radio bursts is just how far they travel to reach us. These signals don't originate in our cosmic backyard. They come from galaxies so distant, their light began its journey when the universe was barely half its current age. Take FRB 190523, detected in 2019. Its home, a massive galaxy nearly 4 billion light-years away. That means the burst we observed had been racing through the void since before Earth even existed. And yet, by the time it arrived, all we caught was a fleeting blip, a whisper from the edge of the observable universe. Pinpointing these extragalactic origins isn't as simple as tracing a cosmic address. FRBs arrive without return labels, forcing astronomers to play interstellar detective. The process starts with radio telescopes, arrays of antennas listening for the faintest whispers across the cosmos. When a burst is detected, the real work begins. Astronomers scramble to triangulate its position using multiple observatories, narrowing down the patch of sky it came from. Only then can optical telescopes swing into action, searching for a host galaxy in that region. But here's the catch: space is crowded. A single degree of sky contains thousands of galaxies, each a potential culprit. The breakthrough comes from a burst's unique fingerprint, a distortion called dispersion. As FRBs traverse the vast stretches between galaxies, they interact with free electrons, slowing down slightly at lower frequencies. The more spread out the signal, the more material it's passed through, revealing its epic journey. This dispersion isn't just a clue, it's a revolutionary tool for mapping the cosmos. The universe isn't empty between galaxies. It's filled with a diffuse fog of ionized gas, so thin it's nearly undetectable by other means. FRBs pierce through this veil, allowing us to measure its density for the first time. Think of it like shining a flashlight through fog. The dimmer the light, the thicker the mist. By analyzing how much an FRB's signal disperses, astronomers can weigh the invisible matter strewn across intergalactic space. Some bursts even hint at cosmic filaments, the sprawling threads of the universe's large-scale structure, where galaxies cluster like beads on a string. But distance isn't just a curiosity, it's a paradox. FRBs are unbelievably bright, often outshining entire galaxies in radio waves for milliseconds. How can something so far away beam such intense energy directly at us? One theory suggests their emission is narrowly focused, like a lighthouse beam sweeping across the cosmos. If Earth happens to lie in its path, we catch a dazzling flash. Miss it by a fraction and the burst slips by unnoticed. This would explain why we detect so few despite the universe presumably teeming with them. The implications stretch beyond astrophysics. If FRBs truly trace the universe's hidden scaffolding, they could refine how we measure cosmic expansion. Discrepancies in dispersion might reveal pockets of missing matter or even exotic physics, dark energy's fingerprints on the fabric of space-time. Every new localized burst adds another data point to our map of the cosmos, turning these enigmatic flashes into cosmic yardsticks. Yet for all their utility, FRBs guard their secrets fiercely. Even with precise host galaxies identified, the exact engines behind them often remain shrouded. Some erupt from serene, ancient galaxies, others from chaotic stellar nurseries. This lack of a consistent birthplace only deepens the mystery. How can the same phenomenon arise in such wildly different environments? The answer might rewrite our understanding of how the universe's most extreme objects behave. For now, each extragalactic burst is both a revelation and a riddle, reminding us that the farther we peer into the cosmos, the more questions we uncover. To grasp the sheer power behind fast radio bursts, consider this: an explosion lasting less than the blink of an eye can unleash as much energy as our sun radiates over months. That's not a miscalculation. In mere milliseconds, these cosmic flashes channel energy equivalent to hundreds of millions of hydrogen bombs detonating in unison. The numbers defy intuition. A typical FRB emits around 10 to the 38th ergs of energy. If we could harness just one burst, it would power human civilization for centuries. Yet the universe produces them effortlessly, like sparks from a celestial forge. So what cosmic furnace could possibly generate such staggering output? Leading theories point to Magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Picture a city-sized object spinning faster than a kitchen blender, its crust under such immense strain that it occasionally fractures, releasing titanic quakes. These starquakes could fling out magnetic shockwaves, accelerating particles to near light speed and producing the bursts we detect. but even Magnetars struggle to explain the most energetic FRBs. Some signals pack enough punch to challenge the limits of known physics, forcing astronomers to consider wilder possibilities. One radical idea involves cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If these threads vibrate or snap, they might release bursts of energy capable of traversing the universe. Others speculate about colliding neutron stars or black holes, where cataclysmic mergers could launch ultra-relativistic jets. The problem: most observed FRBs don't line up with such violent events. Repeaters especially suggest a more stable engine, something that doesn't destroy itself in the process. Then there's the beaming effect. FRBs might not radiate energy in all directions, but instead focus it into ultra-narrow jets, like a cosmic flashlight aimed directly at Earth. This would make their apparent brightness deceptive, a trick of perspective that spares us from confronting even more absurd energy requirements. Yet even with this caveat, the numbers remain jaw-dropping. The real puzzle lies in efficiency. Known astrophysical processes waste enormous amounts of energy as heat or light, but FRBs seem to channel nearly all their power into radio waves, something no natural phenomenon should achieve. Some researchers cautiously float the idea of engineered signals, though natural explanations still hold favor. Until we catch an FRB in the act of forming, its energy source will remain one of the universe's most exhilarating mysteries, a reminder of how much we have yet to learn about the forces shaping the cosmos. Among the thousands of fast radio bursts detected so far, FRB 121102 stands out as the cosmic equivalent of a chattering mystery. This wasn't just the first repeater ever discovered. It was the one that shattered the assumption that all FRBs were one-off fireworks in the dark. Unlike its fleeting cousins, this burst didn't just speak once and vanish. It kept talking, sending out erratic signals that flickered like a radio with a mind of its own. Some bursts arrived in clusters, others spaced apart by weeks or months with no discernible rhythm. It was as if the cosmos had handed us a puzzle with half the pieces missing. Then came the real breakthrough, pinpointing where these whispers were coming from. In 2017, astronomers traced FRB 121102 to a tiny, unassuming dwarf galaxy more than 3 billion light-years away. This wasn't a majestic spiral or a bustling galactic metropolis. It was a cosmic backwater, a place brimming with young stars and turbulent gas. The burst's home seemed to scream instability, a nursery for violent stellar processes. But here's where things got even stranger. Lurking near the FRB's origin point was something unexpected, a faint but persistent radio source humming quietly in the background. This steady radio glow wasn't part of the bursts themselves, but it was always there, like the hum of a distant generator. Some theorists believe it could be a nebula, a cloud of charged particles swirling around a central engine, perhaps a magnetar, one of those ultra-magnetic neutron stars capable of producing sporadic, colossal flares. Others speculate it might be the aftermath of a past cataclysm, like a supernova remnant or a jet from an active black hole. The persistent source's presence hints that FRB 121102 isn't just a random blip, but part of a larger, ongoing cosmic phenomenon. The erratic nature of the bursts only adds to the intrigue. Unlike some later repeaters that follow rough schedules, FRB 121102 fires off in seemingly random spurts. One day, it might unleash a dozen bursts in an hour, then silence for months. This unpredictability suggests whatever's powering these signals isn't a simple, steady mechanism. It's more like a pressure cooker with a faulty valve, occasionally releasing bursts of steam when the internal forces become too much to contain. What makes this repeater especially tantalizing is what it implies about the diversity of FRB sources. If all repeating bursts came from similar environments, we might have a tidy explanation, but they don't. Some repeaters live in calm, aging galaxies, far from the chaotic star-forming regions where FRB 121102 resides. This inconsistency forces us to confront the possibility that multiple cosmic phenomena, some stable, some catastrophic, could be masquerading under the same umbrella of fast radio bursts. The presence of that persistent radio source might be the key. If it's indeed tied to the bursts, it could act like a cosmic fingerprint, revealing the nature of the engine behind them. Magnetars, for instance, are often surrounded by debris and magnetic fields that could produce such a steady hum. But then again, why don't all repeating FRBs have similar counterparts? The absence of a one-size-fits-all answer only deepens the mystery, reminding us that the universe loves exceptions more than rules. FRB 121102's greatest gift might not be the answers it provides, but the questions it forces us to ask. Why do some bursts repeat while others don't? What role does the host environment play in shaping these signals? And what exactly is that faint radio whisper that never goes away? With each new burst it sends, this cosmic enigma challenges our assumptions, proving that in the study of fast radio bursts, every answer seems to unlock 3 more riddles. Among the cosmic suspects behind fast radio bursts, magnetars have emerged as the prime candidate, and for good reason. These aren't your average neutron stars. Imagine a stellar corpse so dense, a teaspoon of its material would weigh 1 billion tons, spinning faster than a blender and wrapped in magnetic fields strong enough to liquefy atoms from 1,000 kilometers away. That's a magnetar, and in 2020, one of them handed astronomers the closest thing to a smoking gun we've ever had. The breakthrough came from our own galactic backyard. On April 28, 2020, a magnetar known as SGR 1935+215, a name only an astronomer could love, erupted in a burst of X-rays and gamma rays. Seconds later, telescopes caught something unprecedented, a fast radio burst dubbed FRB 200428, echoing from the same spot. This wasn't a distant, ambiguous signal. It was happening right here in the Milky Way, and it marked the first time an FRB had been definitively linked to a known astrophysical object. What made this detection so groundbreaking was the sequence. The magnetar's X-ray flare arrived first, a violent rearrangement of its crust under unimaginable magnetic stress. Then came the radio burst, likely produced by shock waves racing through the star's magnetosphere, accelerating particles to near light speed. For theorists, it was like watching a cosmic crime scene unfold in real time. Here was a magnetar long suspected of producing FRBs caught in the act. But there's a twist. FRB 200428 was thousands of times weaker than the extragalactic bursts we've observed. If magnetars are responsible for those distant, far more energetic signals, they'd need to be in a league of their own. Some researchers suggest younger, more active magnetars, ones born in the chaos of supernova or residing in dense stellar nurseries, could pack the necessary punch. Others propose that under extreme conditions, magnetars might unleash giant flares, rare eruptions orders of magnitude more powerful than anything we've seen nearby. The case for magnetars doesn't end there. Their magnetic fields, trillions of times stronger than Earth's, are perfect laboratories for particle acceleration, capable of generating the coherent radio waves that define FRBs. Picture a cosmic particle collider where magnetic chaos whips electrons into frenzied spirals, emitting radio waves like a lighthouse beam. This could explain why some bursts are so intensely focused and why we only detect them when that beam happens to sweep across Earth. Yet mysteries linger. Not all magnetars produce FRBs, and not all FRBs fit neatly into the magnetar mold. Some extragalactic bursts release energy far beyond what even the most extreme magnetars should muster, hinting at unknown physics or entirely different mechanisms at play. Its possible magnetars represent just one flavor of FRB source, with other cosmic catastrophes colliding neutron stars, evaporating black holes, or even more exotic phenomena waiting to be discovered. The discovery of FRB 200428 didn't solve the puzzle so much as hand us a critical piece. It proved that magnetars can produce fast radio bursts under the right conditions, but it also left us wondering just how far those conditions can stretch. Are there magnetars out there with even fiercer magnetic fields, lurking in the hearts of distant galaxies? Or does the answer lie somewhere between known physics and the frontier of our understanding? For now, magnetars remain the best lead in a cosmic whodunit that's far from over. Picture a neutron star spinning so fast, its magnetic field acts like a cosmic hairbrush, raking through surrounding plasma with such precision that it generates perfectly synchronized radio waves. This is the essence of the cosmic comb model, one of the most elegant explanations for how fast radio bursts might form. At its heart lies a simple yet powerful idea. As the star's magnetic field sweeps through dense clouds of charged particles, it forces them into orderly motion like bristles aligning under a comb's strokes. The result, a cascade of electrons moving in unison, emitting radio waves so coherent they arrive at Earth as the sharp, bright pulses we detect. What makes this model so compelling is its ability to explain the extreme focus and intensity of FRBs without invoking exotic physics. The neutron star's rotation and magnetic field work together like a cosmic amplifier, channeling chaotic energy into a narrow, directed beam. Think of it as nature's version of a laser random energy transformed into a synchronized, high-powered signal. This could account for why some bursts appear billions of times brighter than their surroundings, even if their total energy output is modest by cosmic standards. But the cosmic comb isn't without its challenges. For one, it struggles to explain the sheer diversity of FRBs. Repeaters with erratic schedules like FRB 121102 fit neatly into this framework. Their bursts could stem from periodic plasma buildups around the neutron star. Yet the model has a harder time accounting for one-off explosions, especially those with energies that push the limits of known physics. If all FRBs were produced by neutron star combs, why do some resemble cosmic firecrackers while others mimic megaton bombs? Another wrinkle lies in the environment. The cosmic comb requires a very specific setup, a neutron star immersed in a dense plasma cloud, with magnetic fields strong enough to orchestrate particle motion, but not so strong they tear the cloud apart. While magnetars, neutron stars with ultra-powerful magnetic fields fit this bill, not all FRBs trace back to such extreme objects. Some originate in calmer galactic neighborhoods where plasma is sparse, leaving the comb with nothing to brush against. Despite these gaps, the model's elegance keeps it in the running. It offers testable predictions like the presence of low-level radio hums between bursts, akin to the faint static of a comb's teeth grazing plasma. Recent observations of persistent radio sources near repeaters, like the one accompanying FRB 121102, lend weight to this idea. But until we catch a neutron star mid-comb or find a smoking gun linking all FRB types to this mechanism, the cosmic comb remains a tantalizing piece of a much larger puzzle. Perhaps its greatest contribution is reminding us that the universe often crafts its most dazzling phenomena from the simplest ingredients: a spinning star, a magnetic field, and a cloud of particles arranged just so. Even if the cosmic comb doesn't explain every FRB, it reveals how much we still have to learn about the dance between matter and magnetism in the cosmos' most extreme laboratories. When fast radio bursts first crackled onto the scene, astronomers faced a familiar hurdle. Was this truly a cosmic phenomenon, or could it be something as mundane as lightning? Early skeptics pointed to terrestrial radio bursts called lightning-induced whistlers, where electromagnetic energy from storms spirals along Earth's magnetic field lines, producing descending tones. Even closer in character were peritons, quirky signals that mimicked FRBs but were later traced to, of all things, microwave ovens in observatory cafeterias. The challenge was separating celestial whispers from earthly noise, but FRBs refused to fit the lightning mold. Unlike terrestrial bursts which scatter across a range of frequencies, FRBs arrive with a distinctive chirp. Higher frequencies appear milliseconds before lower ones, a telltale sign of intergalactic travel. This dispersion comes from cosmic free electrons stretching the signal, like runners in a marathon slowing at different paces. The farther the burst travels, the more pronounced the effect. Lightning's radio crackles, by contrast, show no such pattern. They're local, impulsive, and confined by Earth's atmosphere. The clincher came with localization. When astronomers traced FRBs to distant galaxies billions of light-years away, the debate was settled. No terrestrial storm, no matter how powerful, could project a signal across such unimaginable voids. The energy demands alone ruled it out. A typical FRB outshines Earth's entire global lightning output by a factor of trillions in mere milliseconds. It's like comparing a firecracker to a supernova. Yet the comparison isn't entirely futile. Studying lightning's radio emissions helped refine detection algorithms, teaching telescopes to filter out cosmic interference. Even peritons, those microwave imposters, served a purpose. They forced observatories to tighten protocols, ensuring only genuine celestial signals made the cut. In the end, FRBs and lightning occupy opposite ends of the radio universe, one a fleeting spark from our own atmosphere, the other a scream from the cosmic dark. There's something deeply unsettling about a signal with no clear origin, like receiving a phone call from a number that doesn't exist. This is the enigma of hostless fast radio bursts, flashes of energy so vivid, yet emerging from patches of sky where no galaxy seems to reside. Take FRB 150215, detected in 2015. Its brilliance suggested a cosmic powerhouse, but when telescopes swiveled to pinpoint its home, they found nothing. No swirling arms of a spiral galaxy, no hazy glow of a distant dwarf, just empty space. Either these bursts are coming from galaxies too faint for our telescopes to see, or they're traveling farther than anything we've ever witnessed. The simplest explanation is that some host galaxies are simply too dim or too distant to spot. Imagine standing in a dark forest trying to find the source of a flashlight beam. If the person holding it is hidden behind thick trees, you might only catch the light itself. Similarly, faint, low-mass galaxies, especially those choked with dust, could be shielding their FRB engines from view. In 2022, the Hubble Space Telescope faced this very challenge with FRB 190724. Initial observations saw no host, but deeper imaging revealed a puny, unremarkable galaxy previously drowned out by cosmic noise. This raises a troubling question. How many other hostless bursts are actually just hiding in plain sight, their galaxies lurking just beyond our current detection limits? But not all cases are so easily resolved. Some FRBs arrive with dispersion measures the stretch in their signals caused by interstellar electrons so extreme, they imply origins far beyond the observable universe's most distant galaxies. That shouldn't be possible, unless, of course, these bursts are bouncing off unseen structures or passing through regions of space denser than we've ever mapped. One provocative theory suggests they might be gravitationally lensed, their paths warped by massive objects like black holes or dark matter clumps, making them appear to come from nowhere. It's as if the universe is projecting cosmic holograms, disguising the true locations of these bursts. Then there's the possibility that some FRBs don't come from galaxies at all. Could they be the death cries of rogue stars, neutron stars flung into the void during galactic collisions, now drifting alone through intergalactic space? These isolated objects, if they exist, might generate bursts when they collide with dense gas clouds or succumb to magnetic instability. Without a host galaxy to anchor them, their signals would arrive like messages in bottles adrift on the cosmic tides. The absence of a host isn't just a technical challenge, it's a clue. If FRBs can emerge from invisible galaxies or the emptiness between them, it forces us to reconsider what we know about cosmic structure. Maybe the universe is dotted with ultra-dark galaxies, their stars too sparse to see but still capable of forging magnetars. Or perhaps intergalactic space isn't as barren as we thought, hiding nomadic objects that occasionally flare into brilliance. Every hostless burst is a reminder that the cosmos still keeps secrets, and some of its most dazzling performances come from stages we can't yet see. Hidden within every fast radio burst is a treasure map, one that doesn't lead to gold, but to something far more valuable, the universe's missing matter. It's called the dispersion measure, and it might be the most important clue FRBs carry. Here's how it works. As these bursts race across the cosmos, they don't travel through perfect emptiness. Instead, they plow through a diffuse sea of free electrons, particles so sparse they're nearly invisible, yet so numerous they leave an imprint on every signal. Higher frequency radio waves zip through slightly faster than their lower frequency counterparts, stretching the burst into a cosmic chirp. The greater the stretch, the more electrons the signal has encountered, revealing the total amount of matter between us and the burst's origin. This isn't just a neat trick of physics, it's solving one of astronomy's most stubborn puzzles. For decades, theories predicted that half the universe's ordinary matter, the baryons making up stars, planets, and us, should reside in vast, diffuse webs between galaxies. But when astronomers added up all the visible stuff, nearly half was missing. Enter FRBs. By analyzing their dispersion measures, researchers realized those lost baryons weren't lost at all. They were hiding in plain sight, floating as ionized gas in intergalactic space, too thin to emit light, yet thick enough to slow radio waves. Each burst acts like a flashlight beam passing through fog. The dimmer it gets, the more material it's traversed. The implications are staggering. Take FRB 180924, which traveled 4 billion light-years before reaching Earth. Its dispersion revealed a precise tally of electrons along its path, confirming the existence of the cosmic web's filamentary structures, threads of gas theorized to connect galaxies like a vast neural network. Without FRBs, mapping this invisible scaffolding would be like trying to trace a city's power grid by counting light bulbs alone. Now, we're not just seeing the glowing nodes, but the wires between them. Yet dispersion measures do more than fill gaps in our cosmic inventory. They expose anomalies. Some bursts arrive with more dispersion than their distance should allow, hinting at dense pockets of matter lurking between galaxies, perhaps clusters of primordial gas untouched since the Big Bang. Others show less, suggesting unexpected voids where the universe's scaffolding has frayed. These deviations could rewrite our understanding of how matter clumps and spreads across cosmic time. The true power of this tool lies in its universality. Unlike traditional methods that rely on light from specific elements, dispersion measures count every free electron in a burst's path, offering an unbiased census of the cosmos's structure. Combine enough FRBs and we could build a 3D map of the universe's hidden matter, not just where it is, but how it's moving, swirling, and evolving. Of course, there are complications. Magnetic fields can twist dispersion patterns, and turbulent plasma near FRB sources can muddy the signal. But as telescopes like CHIME and the upcoming SKA detect thousands more bursts, these wrinkles will smooth out, revealing the universe's skeleton in unprecedented detail. What began as a curious property of radio waves has become a key to unlocking the cosmos's darkest secrets, one dispersed burst at a time. Dark matter has long been the universe's most elusive ghost, invisible, untouchable, yet making up over 80% of all matter in existence. We know it's there by its gravitational pull, but what it actually is remains one of cosmology's greatest unsolved puzzles. Now, imagine if fast radio bursts, those fleeting cosmic flashes, could be the key to finally detecting its presence. It's a radical idea, but one gaining traction among theorists willing to venture beyond conventional astrophysics. At the heart of this hypothesis lies a candidate for dark matter called action's hypothetical particles so light and feeble they've evaded detection for decades. In dense enough clusters, actions might condense into stars, floating like invisible balloons through the cosmos. But when one of these action stars drifts too close to a black hole, something extraordinary could happen. The black hole's gravity would rip the star apart, triggering a cascade of particle conversions. As actions disintegrate, they might briefly transform into bursts of detectable radio waves, signatures that could match the profile of an FRB. It's a cosmic alchemy where the invisible becomes visible, if only for a millisecond. The allure of this theory isn't just its creativity. It neatly addresses two puzzles at once: the staggering energy of some FRBs and the unsettling absence of a visible source. If action stars are collapsing near supermassive black holes in otherwise quiet galactic cores, the bursts would appear to come from nowhere, with no accompanying stellar explosion or magnetar flare. Even the erratic repetition of some FRBs could fit action streams might fragment unpredictably under a black hole's tidal forces, producing sporadic bursts over time. Yet the idea isn't without its skeptics. Critics point out that action-generated FRBs would likely show distinct spectral fingerprints, subtle dips or peaks in their radio waves caused by the particle conversion process. So far, no such signature has been conclusively spotted. Another challenge is timing. Action collapses should produce bursts at predictable energies, while observed FRBs vary wildly in brightness. Still, with hundreds of new bursts being catalogued yearly, the search for these telltale marks is just beginning. Even if actions aren't the answer, the broader principle holds promise. FRBs traverse vast cosmic distances, slicing through regions dense with dark matter. Any interaction, no matter how faint, could leave an imprint on the signal's polarization or dispersion. Some models suggest dark matter might slightly bend FRB radio waves, similar to how a lens distorts light. Others propose that decaying dark matter particles could inject extra energy into the bursts, altering their observed frequencies. Each scenario offers a new way to probe the invisible scaffolding of the universe. What makes this frontier so thrilling is its potential to turn a cosmic mystery into a tool. FRBs might not just be puzzles, they could be the flashlights we've been waiting for, illuminating the dark corners of physics we've struggled to explore. Whether actions, sterile neutrinos, or something even stranger lurks in those shadows, the burst's extreme energy and reach make them ideal messengers from the universe's darkest realms. For now, the connection remains speculative, but in the hunt for dark matter, even the wildest ideas deserve a moment in the spotlight, especially when the universe keeps sending us signals we don't yet understand. Some fast radio bursts refuse to play by the rules, appearing not from fixed points in space, but shifting positions over time as if their sources are wandering through the cosmos. This isn't just a minor anomaly, it's a direct challenge to our most entrenched theories. If FRBs truly come from static objects like neutron stars or magnetars, why would their origins seem to drift? One of the most perplexing cases is FRB 191101, detected in 2019. Initial observations pinned it to a quiet region of its host galaxy, but follow-up studies revealed something unsettling. The burst's apparent origin point had moved. Not by much, just a fraction of an arcsecond, but in cosmic terms, that tiny shift implies the source traveled thousands of astronomical units between bursts. This motion defies expectations. Neutron stars, even hyperactive magnetars, don't just up and stroll across galaxies. They're anchored by gravity, their movements dictated by the slow dance of celestial mechanics. A wandering FRB source suggests something far more dynamic, perhaps a compact object caught in a violent gravitational tango. Picture a neutron star orbiting a black hole, flung around at relativistic speeds during each close pass. Or consider a binary system where one star's explosive death sends its companion careening through space, trailing bursts behind it like cosmic breadcrumbs. Yet there's a catch. The velocities required to explain these shifts border on the absurd. For a source to visibly move over human timescale observations, it would need to be hurtling at a significant fraction of light speed, something only the most extreme astrophysical events could achieve. Some theorists propose superluminal motion, where relativistic jets from a collapsing star appear to move faster than light due to projection effects. Others wonder if we're seeing not the motion of a single object, but the sequential ignition of separate engines along a pre-existing path, like lights flickering on along a freeway. Even stranger are the bursts that emerge from cosmic voids, regions devoid of star formation or visible galactic structure. These aren't just wandering, they're seemingly orphaned, with no stellar nursery or dense environment to power them. One leading hypothesis suggests they could be triggered by rare, high-velocity compact objects, rogue neutron stars or black holes ejected from their birth galaxies during violent mergers. Stripped of surrounding gas and dust, these loners might only flare when they occasionally plow through sparse intergalactic clouds, creating bursts as fleeting as they are mysterious. The implications ripple outward. If FRB sources can move, it complicates efforts to trace them back to host galaxies or correlate them with other cosmic events. It also raises the possibility that some one-off bursts might actually be repeaters in disguise, their apparent motion simply making them harder to pin down. Most tantalizingly, wandering FRBs hint at entirely new classes of astrophysical objects, celestial nomads too faint to see directly, yet capable of unleashing titanic radio flashes when conditions align. What's clear is that these restless signals refuse to fit neatly into any single box. They challenge us to rethink not just what FRBs are, but how the universe's most energetic phenomena might hide in plain sight, not as fixed points on a map, but as phantoms slipping through the cosmic dark. If you tuned your radio to different stations, you'd expect the same song to play across all frequencies, just clearer on some than others. Fast radio bursts defy that logic. Some of these cosmic signals appear only at specific frequencies, vanishing completely when observed outside their narrow radio sweet spots. It's as if the universe has invisible filters, selectively blocking certain wavelengths while letting others through untouched. Take FRB 180916, a repeater that fires off bursts almost exclusively between 400 and 800 MHz, like a cosmic radio station broadcasting on a single, mysterious channel. This frequency-dependent behavior isn't just a curiosity, it's a fingerprint of the burst's environment and the physics powering it. One explanation points to plasma lenses, dense clouds of ionized gas floating between galaxies. As an FRB's radio waves traverse these clouds, they can bend and scatter, much like light flickering through rippling water. Certain frequencies might align perfectly to slip through, while others destructively interfere, effectively erasing parts of the signal. Imagine shouting through a fan. Some sound waves hit the blades and vanish, while others pass through cleanly. But plasma lenses alone can't explain the full picture. Some bursts show multiple emission bands popping up at distinct frequencies with dead silence in between. This suggests something far more intricate is happening at the source itself. Magnetars, for instance, could be emitting radio waves in tightly focused beams where only specific frequencies escape their chaotic magnetic fields. Picture a lighthouse where the glass prism fractures light into discrete colors only here. The prism is a neutron star's magnetosphere, splitting radio waves into isolated frequency bands. Then there's the possibility of synchrotron absorption, a process where high-energy electrons in the FRB's path gobble up certain wavelengths like a cosmic buffet. The result, a signal that's been selectively nibbled at, leaving gaps in its frequency profile. This could explain why some bursts appear scalloped, their energy dipping at predictable intervals across the radio spectrum. The most tantalizing clue comes from bursts that change their frequency behavior over time. FRB 121102, for example, began its life as a low-frequency repeater before suddenly firing off bursts at higher energies years later. This evolution hints at a dynamic engine, perhaps a magnetar's magnetic field decaying, or its surrounding plasma environment shifting like storm clouds clearing after a downpour. What makes these frequency puzzles so valuable is their diagnostic power. By studying which wavelengths make it to Earth and which don't, astronomers can reverse engineer the conditions inside FRB sources and the cosmic highways they traverse. It's like analyzing the stains on a filter to deduce what flowed through it. Every missing frequency band is a breadcrumb leading us closer to understanding how these bursts are born, how they survive their epic journeys, and why they insist on playing the universe's most enigmatic game of cosmic hide and seek. Among the many clues hidden within fast radio bursts, few are as telling as the twists in their light, subtle spirals that reveal the influence of some of the universe's most extreme magnetic fields. When astronomers analyzed FRB 180301, they noticed something extraordinary. Its radio waves weren't just flickering, they were corkscrewing through space, their polarization rotating in a way that defies simple explanation. This kind of twisting, known as Faraday rotation, doesn't happen randomly. It's the cosmic equivalent of a fingerprint left by powerful magnetic fields, the kind found only in the most violent corners of the universe. What makes this polarization so revealing is the sheer scale of the forces required to imprint it. For an FRB's radio waves to spiral this dramatically, they must have passed through, or originated within, a magnetic environment of almost unimaginable intensity. Picture a neutron star so magnetized, its field could strip the electrons from atoms thousands of kilometers away. Now imagine that field fluctuating wildly as the star's crust quakes or as it orbits a companion black hole, each convulsion twisting the radiation it emits like a cosmic kaleidoscope. That's the kind of scenario that could produce the polarization signatures we're seeing, but there's a catch. While magnetars can generate these extreme fields, not all polarized FRBs fit neatly into that box. Some show rotation measures the degree to which their polarization twists so high, they imply environments even more extreme than anything around known neutron stars. This has led theorists to consider black hole magnetospheres, where magnetic fields become so tightly wound by the black hole's spin, they act like particle accelerators on a galactic scale. In these regions, plasma and magnetism churn at relativistic speeds, potentially imprinting FRBs with polarization patterns unlike anything seen in quieter cosmic settings. The polarization of FRB 180301 adds another layer to this mystery. Unlike some bursts with stable, predictable twists, this one's polarization varied dramatically between bursts, as if the magnetic landscape around its source was shifting in real time. One explanation, a neutron star wobbling precariously as it orbits a massive companion, its magnetic axis tilting chaotically with each rotation. Another possibility involves a black hole's accretion disk, where clumps of magnetized plasma might intermittently eclipse the FRB source, filtering its light through ever-changing magnetic lenses. The implications stretch beyond mere curiosity. Polarized FRBs could serve as cosmic probes, letting us map magnetic fields in regions too distant or violent to study by other means. Every twist in their light carries information about the density, turbulence, and structure of the matter they've traversed data we can't gather any other way. It's as if the universe handed us a toolkit for measuring its most hidden forces, using bursts of radio waves as our ruler. Yet for all their diagnostic power, these polarized signals also deepen the central mystery. If some FRBs are forged in magnetic maelstroms this extreme, why do others show barely any polarization at all? Could there be multiple pathways to producing these bursts, some from orderly magnetar flares, others from the chaotic shredding of stars by black holes? The answer might lie in the growing catalogue of FRBs, each polarized burst adding another piece to a puzzle we're only beginning to assemble. One thing is certain, wherever these twisted signals are coming from, they're painting a picture of a universe far more magnetically wild than we ever imagined. The famous WOW signal detected in 1977 remains one of astronomy's most tantalizing mysteries. A 72-second burst of radio waves so powerful, the astronomer who found it scribbled, "Wow." In the margin of the printout, for decades, it stood as the gold standard of potential extraterrestrial signals, a fleeting blip that seemed too artificial to dismiss but too brief to confirm. Fast radio bursts share an eerie similarity. Both are transient, enigmatic, and pack enough energy to ignite scientific imaginations. Yet while the WOW signal faded into legend without repetition, FRBs have become a cosmic constant, forcing us to confront an uncomfortable truth. Nature might be far better at impersonating intelligence than we ever guessed. What sets the WOW signal apart is its narrowband frequency, a hallmark of engineered signals, not natural astrophysical events. Most cosmic phenomena emit across wide swaths of the spectrum, like a radio tuned to static. The WOW signal, by contrast, appeared almost laser-focused at 1420 MHz, a frequency coincidentally matching the emission line of hydrogen, the universe's most abundant element. It was as if someone had shouted into the cosmic void using the universe's native language. FRB, however, are broadband bursts spanning hundreds of megahertz, a trait far more consistent with violent celestial processes like magnetar flares or collapsing neutron stars. But the parallels don't end there. Both signals arrived from seemingly empty patches of sky, with no obvious astrophysical source to explain them. The WOW signal originated near the Chi Sagittarii star group, a region devoid of known exoplanets or unusual stellar activity. Early FRBs, too, appeared orphaned, their host galaxies invisible until years later. This shared ambiguity fueled speculation. Could these be deliberate beacons, or at least technosignatures from advanced civilizations? The difference lies in scale. While the WOW signal was a solitary event, FRBs now number in the thousands, distributed across the cosmos with a frequency that strains the aliens hypothesis. If extraterrestrials are behind them, they'd need to be everywhere all at once, orchestrating a synchronized radio symphony across billions of light years. Still, FRBs have inadvertently given SETI researchers new tools and hope. Their extreme brightness means they could, in theory, be used as interstellar radar pulses intentionally aimed to announce a civilization's presence. Some theorists suggest advanced societies might even harness magnetars as lighthouses, manipulating their magnetic fields to encode information in bursts. A handful of FRBs exhibit odd spectral features, narrowband spikes or periodicities that, while likely natural, are just the sort of anomalies SETI scientists would pounce on. The lesson here isn't that FRBs are signals from aliens, but that they've expanded our understanding of what cosmic noise can look like. If nature can produce something this artificial seeming, how many other cosmic oddities have we dismissed too quickly? Perhaps the most profound impact FRBs have had on SETI is philosophical. They've shown us that the universe is capable of generating signals so precise, so energetic, that they blur the line between natural and artificial. The WOW signal, once a lonely outlier, now feels like part of a broader pattern, one where the cosmos constantly teases us with phenomena that defy easy categorization. In that sense, FRBs haven't closed the book on SETI, they've rewritten it. every new burst is a reminder that the universe is stranger than we imagine, and that somewhere in the static there might still be a signal waiting to be understood. Imagine a cosmic magnifying glass warping the fabric of space itself to bend light, or in this case, radio waves into something brighter and stranger than it originally was. This is the heart of the lens hypothesis for fast radio bursts, the idea that some of these signals might be passing through gravitational lenses on their way to Earth. Just as a glass lens can focus sunlight into a burning point, massive objects like black holes or galaxy clusters could be distorting and amplifying FRBs, turning what might have been faint whispers into deafening cosmic shouts. The implications: some bursts we detect might not reflect their true brightness at all. They could be cosmic mirages, their signals artificially enhanced by the universe's own funhouse mirrors. The concept isn't purely theoretical. We already see gravitational lensing in action with light, where massive foreground objects bend the light from more distant galaxies into arcs, rings, or even multiple images. The same physics should apply to radio waves. If an FRB's path happens to graze a black hole or dense cluster of dark matter, space-time itself would act like a lens, potentially splitting the burst into several copies arriving at slightly different times. In fact, some repeating FRBs exhibit odd quirks, bursts with nearly identical dispersion measures but slightly varying arrival times or brightnesses that could hint at this very phenomenon. It's as if the universe is hitting replay on the same signal, but with the volume knobs tweaked each time. One of the most compelling cases for lensing comes from FRBs that seem too bright to be true. Take FRB 190523, a burst so energetic that, if unlensed, it would require a source beyond anything we've observed in nature. But if its path were bent by an intervening supermassive black hole, the burst's true energy might be far more modest, just amplified by the lens's colossal gravity. This would solve a persistent puzzle: how some FRBs appear to violate theoretical energy limits for known astrophysical processes. They might not be breaking the rules at all, just benefiting from cosmic cheating. Even more intriguing is the possibility of caustic crossing, where an FRB source moves relative to a lens, causing its brightness to spike or fade dramatically as it traverses regions of extreme magnification. This could explain why some repeaters show erratic intensity swings between bursts. Their alignment with the lens might be shifting, turning the cosmic volume knob up or down unpredictably. Telescopes have caught similar behavior in lensed quasars, their flickering light warped by foreground galaxies. If FRBs are undergoing the same process, it would mean we're not just studying the bursts themselves, but the invisible structures bending their path. Yet proving lensing isn't straightforward. To confirm it, astronomers need to spot the lens itself, a daunting task when dealing with objects as faint as primordial black holes or dark matter clumps. Some researchers are hunting for subtle distortions in FRB host galaxies, searching for the gravitational fingerprints of unseen lenses. Others analyze burst profiles for telltale signatures of lensing, like duplicated waveforms or frequency-dependent delays. So far, no smoking gun has emerged, but with FRB detection rates soaring, the odds of catching a lensed burst in action are improving daily. What makes the lens hypothesis so powerful is its dual role. It could explain some of FRB's most baffling properties while turning them into tools for probing the universe's hidden architecture. Every lensed burst would offer a free snapshot of the warped spacetime it traversed, revealing the mass and distribution of otherwise invisible matter. It's a reminder that in astronomy, even anomalies can become instruments, cosmic quirks repurposed as keys to unlock deeper mysteries. Whether lensing explains one FRB or 1,000, the very possibility stretches our imagination, showing once again how the universe bends not just light, but our understanding of what's possible. Every fast radio burst carries hidden information about the vast cosmic highways it travels, an imprint of the invisible material stretching between galaxies. Astronomers have begun harnessing this data like cosmic mile markers, using FRBs to map the universe's structure with unprecedented precision. The secret lies in dispersion measures, the subtle stretching of a burst's radio waves as they pass through free electrons scattered across intergalactic space. The more a signal disperses, the more matter it's encountered, offering a direct way to weigh the universe's otherwise undetectable scaffolding. Take FRB 180924, whose journey spanned 4 billion light-years. By analyzing how its frequencies spread out during transit, researchers calculated the density of ionized gas along its path, material so diffuse it's invisible to traditional telescopes. This method revealed filaments of the cosmic web, the sprawling network of gas connecting galaxies like threads in a tapestry. Unlike older techniques that relied on light absorption from quasars, FRBs provide a cleaner measurement, unaffected by the quirks of individual galaxies or foreground objects. They act as universal probes, painting a three-dimensional map of where and how much matter lingers in the voids, but the ambition doesn't stop there. Some cosmologists believe FRBs could help resolve the most pressing tension in modern astronomy: the Hubble tension, a stubborn discrepancy in measurements of the universe's expansion rate. Traditional methods like tracking distant supernova or the cosmic microwave background disagree by roughly 10%, a gap that might hint at unknown physics. Dispersion measures offer a third way, since the amount of stretching in an FRB signal depends on both distance and the density of intervening matter. A large enough sample could independently calculate expansion rates. The trick is assembling a catalog of bursts with pinpointed origins, something observatories like CHIME and the upcoming Square Kilometre Array are making possible. Already, early studies show promise. By comparing dispersion measures of FRBs at different distances, astronomers have spotted slight anomalies, regions where matter clumps more densely than standard models predict. These could be signatures of dark matter's gravitational pull or even relics from the universe's inflationary phase. Other bursts pass through unusually sparse voids, challenging assumptions about how smoothly matter is distributed. Each deviation is a clue, refining our understanding of cosmic evolution. What makes FRBs uniquely powerful as yardsticks is their neutrality. Unlike light, which interacts with dust and gas in complex ways, radio waves pierce nearly everything undisturbed, recording a pristine snapshot of their journey. Future telescopes detecting thousands of bursts could turn this advantage into a revolutionary tool, one that not only maps the universe's hidden matter, but also tests theories about dark energy, quantum gravity, and the fate of the cosmos itself. For astronomers, every FRB is more than a mystery. It's a ruler etched into the fabric of space, waiting to be read. The idea that fast radio bursts could be signals from an advanced extraterrestrial civilization is undeniably thrilling, like something straight out of science fiction. When you consider their mind-bending energy, precise frequency ranges, and unpredictable patterns, it's tempting to wonder, what if these aren't natural phenomena at all? What if they're deliberate transmissions, cosmic lighthouses built by civilizations far beyond our own? This tantalizing possibility exploded into public consciousness after the discovery of FRB 121102's repeating bursts, with some researchers cautiously suggesting its irregular pattern bore eerie similarities to an engineered signal. But before we leap to interstellar conclusions, let's apply a principle scientists rely on daily: Occam's razor. Simply put, the simplest explanation that fits the facts is usually the right one. And the facts so far point overwhelmingly to natural astrophysical origins. Magnetars, colliding neutron stars, and black hole eruptions, all known cosmic phenomena, can account for FRBs without invoking interstellar engineering. Even the repeating patterns have plausible explanations, like a wobbling neutron star's magnetic field flickering on and off as it orbits a companion. Nature, as it turns out, is perfectly capable of producing signals that seem artificial without any intelligence behind them. That said, dismissing the alien beacon hypothesis outright would be a missed opportunity, not because it's likely, but because it pushes us to test the boundaries of what we know. Historically, many cosmic mysteries initially attributed to aliens like pulsars, whose precise pulses were once nicknamed LGM signals for little green men, were later explained by natural processes. Yet the mere act of considering extraterrestrial origins forced scientists to sharpen their methods, refining how they distinguish natural from artificial signals. FRBs now serve a similar role, challenging astronomers to develop tools sensitive enough to spot genuine anomalies. One compelling argument against the beacon theory is sheer numbers. FRBs occur constantly across the universe. Estimates suggest thousands happen daily. For them to be artificial, countless civilizations would need to be broadcasting similar signals in perfect synchrony across billions of light years. Statistically, that stretches credulity. Even more damning, their energy requirements. Some FRBs emit more power in milliseconds than humanity's entire energy output over centuries. If aliens are behind them, they'd need Kardashev-scale megastructures, engineering feats so advanced they defy our understanding of physics. Yet the allure persists, and there's value in that. The search for extraterrestrial intelligence has always been as much about philosophy as science, a way to grapple with humanity's place in the cosmos. FRB, by pure coincidence, happen to share traits we'd expect from a deliberate beacon. They're bright, transient, and detectable across interstellar distances. That makes them unintentional test cases for SETI, even if their origins are natural. Some researchers have combed through FRB data for signs of encoding narrowband spikes or mathematical patterns, but so far, nothing conclusive has emerged. What's fascinating is how this debate reveals our own biases. Humans are pattern-seeking creatures. We're wired to find meaning in randomness. When faced with something as enigmatic as an FRB, it's almost reflexive to anthropomorphize it, to imagine a sender behind the signal. That instinct isn't wrong, it's just incomplete. The universe is stranger than we can imagine, and sometimes the truth outstrips even our wildest speculations. Whether FRBs are natural or not, they've already expanded our imagination of what's possible, and that in itself is a gift. The beacon hypothesis may fade, but the questions it raises will linger, pushing us to look deeper, think broader, and stay humble in the face of the cosmos mysteries. The discovery of FRB 200428 wasn't just a milestone, it was a cosmic curveball. Unlike every other fast radio burst detected before it, this one didn't come from some distant galaxy billions of light years away. It erupted inside our own Milky Way, a mere 25,000 light years from Earth, and for the first time, astronomers could pinpoint its source with certainty. A magnetar known as SGR 1935 plus 215. Here was proof, undeniable and close to home, that at least some FRBs could be tied to these ultramagnetic stellar corpses. But this revelation only deepened the mystery. If magnetars in our galaxy create FRBs, why do the vast majority of these signals still hail from the far reaches of intergalactic space? The Milky Way magnetar connection should have been a eureka moment, a key to unlocking FRBs across the universe. Instead, it exposed a glaring inconsistency. FRB 200428 was thousands of times weaker than its extragalactic cousins. Its energy output, while impressive by human standards, paled next to bursts like FRB 190523, which unleashed enough power to outshine entire galaxies. This discrepancy suggests two possibilities. Either local magnetars are fundamentally different from their extragalactic counterparts, or we're missing something critical about how these cosmic engines scale. Perhaps younger, more violent magnetars, once freshly forged in supernova or orbiting black holes, can produce far more energetic bursts. Or maybe the intergalactic ones benefit from some unseen cosmic amplifier, like gravitational lensing or cascading particle collisions in dense plasma clouds. Another puzzle is rarity. Despite the Milky Way housing dozens of known magnetars, FRB 200428 remains the only confirmed homegrown fast radio burst on record. Statistically, that's bizarre. If magnetars regularly produce FRBs, we should detect more of them locally, where signals don't have to traverse billions of light years to reach us. One explanation is observational bias. Our telescopes might be missing weaker bursts drowned out by Earth's radio noise, or brief signals that slip through the gaps between observations. But even accounting for these limitations, the scarcity holds. It's as if our galaxy's magnetars are whispering while those in distant galaxies are screaming. This imbalance points to an unsettling truth: not all magnetars are created equal. The ones generating extragalactic FRBs could exist in environments far more extreme than anything in our galactic neighborhood. Picture a magnetar born from the collision of two neutron stars, its magnetic field turbocharged by the violence of its creation, or one orbiting a supermassive black hole, its crust constantly stressed by tidal forces. These exotic scenarios might push magnetars beyond their usual limits, turning them into FRB factories capable of the universe's most powerful radio blast. Meanwhile, our Milky Way's magnetars, while impressive, might simply lack the right conditions to reach those extremes. Yet the most tantalizing possibility is that we're witnessing selection bias on a cosmic scale. The FRBs we detect across the universe are the brightest of the bright, the ones powerful enough to cross unimaginable distances and still stand out against the noise. For every one of those, there could be thousands of weaker bursts like FRB 200428 that fade into the background before they ever reach us. In this view, the Milky Way isn't strangely quiet. It's just showing us the baseline, while the extragalactic bursts represent the explosive outliers. What makes FRB 200428 so valuable isn't just what it explains, it's what it complicates. By proving magnetars can produce FRBs, it narrows the field of potential sources. But by highlighting how different it is from most bursts, it reminds us that the universe rarely follows a single rulebook. Every detection peels back another layer, revealing a cosmos more varied and unpredictable than we ever imagined. Whether the answer lies in undiscovered physics, hidden cosmic environments, or sheer observational luck, one thing is certain: the story of fast radio bursts is far from over. And sometimes the most revealing clues come not from the distant reaches of space, but from our own galactic backyard. Some of the universe's most violent deaths might leave behind more than just rubble. They could be the birthplaces of fast radio bursts. The supernova afterglow theory suggests that long after a star explodes, its shockwaves and remnants might still be generating energetic radio flashes, like cosmic fireworks with an unexpected encore. The idea hinges on what happens in the chaotic years following a supernova, when the collapsing star's debris races outward at nearly light speed, plowing into interstellar gas and creating turbulent electromagnetic storms. Consider Cassiopeia A, the remnant of a supernova that lit up Earth's skies around 300 years ago. Today, it's a churning cauldron of magnetic fields and accelerated particles, emitting radio waves so intense they outshine most other sources in our galaxy. While not an FRB itself, it illustrates how supernova remnants can remain energetic long after the initial explosion. Now imagine a similar scenario, but with conditions dialed to extremes: a rapidly rotating neutron star embedded in a dense cloud of its own debris, its magnetic field whipping particles into frenzied motion. Under the right circumstances, shocks from colliding ejecta or sudden magnetic reconnection events could launch bursts of coherent radio emission, essentially turning a stellar corpse into a sporadic radio beacon. The theory gains traction when examining certain FRB host galaxies. Many reside in regions rich with recent star formation, where massive stars live fast, die young, and leave behind volatile remnants. FRB 120128, for instance, erupted from a dwarf galaxy teeming with young stars, the type of environment where supernova frequently seed their surroundings with magnetars and turbulent plasma. Even more telling, some bursts exhibit polarization patterns consistent with radiation traversing the twisted magnetic fields expected in supernova remnants. It's as if the radio waves are picking up fingerprints from the very structures that shaped them. Yet challenges remain. Most supernova remnants produce steady radio glow, not the millisecond scale spikes that define FRBs. To bridge this gap, theorists propose lightning in a nebula, localized instabilities where shock fronts or collapsing magnetic bubbles create fleeting, intense emission zones. Picture a storm cloud crackling with discrete lightning bolts amidst constant thunder. Similarly, a supernova remnant might generate both persistent background noise and sporadic, high-intensity bursts when conditions align just right. The clincher will be catching an FRB in a supernova remnant we've already mapped, a task easier said than done given how quickly these bursts fade. But with next-generation telescopes monitoring nearby remnants around the clock, the odds of spotting a connection are improving. If verified, the supernova afterglow theory would add a poignant twist to these cosmic explosions, proving that even in death, stars can still send signals across the void, not with a bang, but with a brilliant, fleeting whisper. Fast radio bursts don't just vary in brightness, they seem to cluster into two distinct camps, as if the universe has two separate factories manufacturing these signals. On one side, there are the faint repeaters, flickering with bursts a million times weaker than their more explosive cousins. On the other, the titanic one-offs, vanishing in flashes of energy so intense, they outshine entire galaxies. This bimodal split isn't random noise. It's a cosmic fingerprint hinting at two fundamentally different engines powering these phenomena. The first group repeaters like FRB 121102 behave like cosmic campfires, crackling with bursts that rarely exceed 10 to the 38 ergs of energy. Their emissions are erratic but frequent, often accompanied by persistent radio glows and linked to turbulent star-forming regions. Then there's the other extreme, bursts like FRB 150807, which detonated with a staggering 10 to the 42 ergs, equivalent to the sun's output over weeks compressed into milliseconds. These monsters haven't been caught repeating, and they tend to originate in calmer, more evolved galaxies. The gap between these groups isn't a smooth continuum, it's a chasm, as if nature has a switch flicked to two entirely different settings. What could explain this divide? The leading theory points to distinct progenitor populations. Repeaters might stem from magnetars, neutron stars with crusts that sporadically fracture under magnetic strain, releasing manageable but recurring flares. Their lower energy output fits within known physics for these objects, especially if their bursts are narrowly beamed toward Earth, but the one-offs. They defy magnetar limits. Instead, they align with cataclysmic, one-time events like neutron star mergers or collapsing black holes processes that unleash energies orders of magnitude higher. Picture the difference between a sparkler and a stick of dynamite. One sizzles, the other obliterates. Yet even this tidy explanation has wrinkles. Some repeaters, like FRB 180916, occasionally lob bursts into the higher energy range, blurring the line between the two groups. Meanwhile, a handful of one-offs have been tentatively linked to magnetar-rich environments, muddying the clean separation. This overlap suggests that the bimodal distribution might not be absolute, just a dominant trend with exceptions whispering of hybrid mechanisms or transitional states. Perhaps some magnetars, under extreme conditions, can occasionally mimic the power of a cataclysm, or maybe certain mergers leave behind unstable remnants that sputter repeating flares. The bimodal split could also reflect something deeper about emission physics. repeaters might tap into magnetic reconnection, a process where tangled field lines snap and realign, releasing energy in bursts akin to solar flares. One-offs, by contrast, could arise from relativistic shocks where material accelerated to near light speed slams into surrounding gas, creating a single, devastating radio blast. The two processes operate on fundamentally different timescales and energy budgets, naturally producing the observed dichotomy. What makes this puzzle so compelling is what it reveals about the universe's creativity. Fast radio bursts aren't a monolithic class, they're a cosmic spectrum with distinct lineages and triggers. The bimodal distribution isn't just a curiosity, it's a roadmap guiding us toward the realization that these signals might be multiple phenomena wearing the same mask. As telescopes uncover more bursts, the dividing line may sharpen or dissolve, but for now, it stands as one of FRBs' most tantalizing clues, a proof that in the study of the cosmos, even the loudest signals sometimes speak in dual tongues. Most cosmic phenomena obey a predictable rhythm. Supernova fade over weeks, pulsars tick like celestial metronomes, even black holes devour matter in steady, measurable gulps. Fast radio bursts shatter this expectation with their capricious nature, but nothing defies the rules quite like an FRB storm, a sudden, violent eruption where a single source spits out dozens of bursts in mere hours. In the fall of 2019, astronomers witnessed this firsthand when FRB 121102, already the most prolific repeater known, unleashed a barrage of over 100 bursts in just 47 days, with 21 crammed into a single 60-minute window. It was as if the universe had flicked a switch, transforming a sporadic whisper into a deafening roar. These storms are more than just cosmic fireworks, they're windows into the extreme physics powering FRBs. The sheer density of bursts rules out one-time cataclysms like neutron star collisions. Instead, they point to an engine capable of storing and releasing energy in rapid, erratic bursts, like a pressure cooker hissing steam through a faulty valve. Magnetars remain the prime suspect, but their traditional models struggle to explain such frenzied activity. Typical starquakes or magnetic reconnection events shouldn't produce dozens of flares in quick succession unless something far more dynamic is at play. Perhaps a magnetar caught in the act of magnetic field restructuring, its crust fracturing like tectonic plates in a non-stop earthquake. The tempo of these outbursts holds tantalizing clues. During its storm phase, FRB 121102's bursts arrived in clusters, with some separated by just milliseconds too fast for a single emission region to recover and recharge. This suggests multiple, independent spark plugs firing within the same cosmic engine. Picture a neutron star's surface riddled with magnetic hotspots, each snapping like overstretched rubber bands under the star's unbearable spin and gravity. Every snap releases a burst, with the storm representing a cascade of these micro-explosions rippling across the star's crust. What's even stranger is what these storms don't show. Despite their intensity, the individual bursts within a storm don't grow progressively stronger or weaker. They flicker on and off like a faulty neon sign, with no clear buildup or wind down. This lack of pattern hints at a system balanced on a knife's edge, where energy input and output reach a precarious equilibrium. One theory posits a reservoir and release mechanism, perhaps a swirling disk of plasma around the magnetar that accumulates material until critical thresholds are crossed, triggering avalanches of particle acceleration. The aftermath of these storms deepens the mystery. FRB 121102's activity didn't end with a bang but a whimper, fading back into a regular sputtering over weeks. Yet its persistent radio glow, the steady hum that shadows its bursts, remained unchanged, as if the underlying power source was unfazed by the radio frenzy. This disconnect implies that whatever produces the storm isn't the same phenomenon maintaining the background glow. The bursts might be surface-level spasms, while the persistent emission stems from deeper, more stable processes, like thunderstorms flashing across a planet's surface while its core churns steadily beneath. Storms like these force us to rethink fundamental assumptions. If a single FRB source can transition from silence to hyperactivity and back without warning, what does that say about the thousands of quieter bursts we've catalogued? Are they merely the faint echoes of storms we missed, or do they represent entirely different modes of operation? The answer might lie in the gaps between outbursts, the quiet periods where the engine is reloading unseen. With every storm we catch, we're not just witnessing a cosmic tantrum, we're decoding the instruction manual of a universe that refuses to play by the rules. Among the universe's most violent mergers, few events rival the cataclysmic dance of colliding neutron stars. These ultra-dense stellar corpses, each packing a sun's worth of mass into a city-sized sphere, unleash gravitational waves, gamma-ray bursts, and glowing kilonovae when they finally spiral together. But could they also be the hidden engines behind some fast radio bursts? The idea isn't as far-fetched as it might seem. When two neutron stars collide, the resulting firestorm doesn't just produce gold and platinum, it creates conditions so extreme they might generate the perfect storm for an FRB. Consider the aftermath of GW 170817, the first neutron star merger detected via gravitational waves in 2017. That event produced a kilonova, a transient glow fueled by radioactive decay, and a short gamma-ray burst, but no FRB was observed. At first glance, that absence seems damning, but here's the twist. The merger happened just 130 million light-years away, well within our detection range for an FRB. If neutron star collisions routinely produced these radio flashes, we should have caught one. Yet the silence might be deceiving. Not all mergers are created equal. The angle of the collision, the star's magnetic fields, and even the density of surrounding matter could determine whether an FRB is beamed our way or lost in the cosmic static. The physics at play here border on the surreal. As neutron stars merge, their ridiculously strong magnetic fields exceeding 1 trillion times Earth's get twisted into impossible configurations. In the chaos, relativistic jets may punch through the debris, and if those jets encounter surrounding plasma, they could generate coherent radio emission through synchrotron maser action. Picture a supersonic jet plowing through a cloud. The shockwaves create intense, focused radiation. In this case, the jet is a stream of particles moving at nearly light speed, and the cloud is the shredded remains of the neutron stars themselves. The result, a millisecond burst of radio waves bright enough to cross the universe. Yet there's a glaring puzzle. Kilonovae and gamma-ray bursts release energy across the electromagnetic spectrum, while FRBs are narrowly concentrated in radio frequencies. If neutron star mergers produce both, why don't we always see them together? One possibility is beaming. FRBs likely emit radio waves in tight cones like a laser pointer, while gamma rays and kilonovae flood outward in all directions. If Earth isn't aligned with the FRB's narrow beam, we'd miss the radio flash entirely even as the broader fireworks dazzle our telescopes. Another factor could be timing. FRBs might only emerge during specific phases of the merger, perhaps in the initial seconds when magnetic reconnection is most violent, or hours later when shockwaves hit distant debris. The most tantalizing evidence comes from FRB 190523, a one-off burst with energy consistent with a neutron star merger's theoretical output. Its host galaxy, a massive, relatively old system, matches the expected environment for such collisions, where stellar survivors have had time to drift into deadly orbits. Unlike magnetar-rich star-forming regions, this calm, evolved galaxy hints at a different engine. Not a young magnetar's tantrum, but the final scream of two neutron stars locking in a fatal embrace. Still, the case remains circumstantial. Until we catch an FRB coinciding with a gravitational wave chirp or a kilonova's glow, the connection stays speculative. Future observatories like the Square Kilometre Array or next-gen gravitational wave detectors could settle the debate by scanning merger sites for radio bursts in real time. If even a handful of events line up, it would rewrite our understanding of these cosmic collisions not just as forges of heavy elements, but as potential factories for the universe's most enigmatic signals. Until then, neutron star mergers stand as both a compelling suspect and a reminder of how much we still have to learn about the chaos lurking in the cosmos' darkest corners. Some of the most radical explanations for fast radio bursts don't come from astrophysics at all. They emerge from the fringes of theoretical cosmology, where the very fabric of space-time might hide defects left over from the universe's birth. Enter cosmic strings, hypothetical one-dimensional cracks in reality, thinner than a proton yet denser than a mountain range, stretching across the cosmos like invisible razor wires. According to some models, when these strings snap or vibrate, they could unleash bursts of energy so intense they'd register as FRBs across billions of light years. The concept stems from the early universe, moments after the Big Bang, when space-time underwent rapid phase transitions, shifts akin to water freezing into ice. Just as ice forms cracks as it solidifies, these transitions might have left behind topological defects, cosmic strings, domain walls, or monopoles. Strings, if they exist, would be unimaginably dense, with a single centimeter weighing more than entire planets. Their immense tension could cause them to oscillate violently, occasionally releasing gravitational waves or electromagnetic radiation as they vibrate. Under the right conditions, those emissions might manifest as the brief, brilliant radio flashes we detect as FRBs. What makes this idea compelling is its ability to explain FRBs' most puzzling traits. Cosmic strings wouldn't be anchored to galaxies, allowing bursts to appear hostless, as some do. Their vibrations could produce both one-off events if a string snaps or repeaters if it oscillates periodically. Even the burst's staggering energy fits. Strings convert mass directly into radiation via Einstein's E=mc², with no need for stellar engines or magnetic fields. The challenge: no one's ever detected a cosmic string directly. They're ghosts in the equations of quantum field theory, predicted but unproven. Still, FRBs offer a potential way to test their existence. If strings are behind some bursts, those signals should carry unique imprints like step-like frequency cuts from cusps, points where strings fold back on themselves, or double-peaked bursts from string loops collapsing. Some FRBs already show odd spectral features that resist conventional explanations, leaving room for exotic possibilities. Skeptics argue that cosmic strings are a solution in search of a problem, an elegant idea lacking empirical support. Yet history shows that cutting-edge physics often begins as speculation. Dark matter and gravitational waves were once considered fringe, now they're pillars of cosmology. Whether cosmic strings explain FRBs or not, their inclusion in the debate stretches our imagination, reminding us that the universe's deepest mysteries might not lie in the stars, but in the invisible scaffolding stitching reality itself together. Radio telescopes should, in theory, catch fast radio bursts across a wide spectrum from the lowest frequencies our instruments can detect to the highest. But here's the oddity: almost no FRBs have been recorded below 400 MHz. It's as if something's snipping off the bottom end of the cosmic radio dial, leaving astronomers to wonder whether the silence is a quirk of our technology, a cosmic veil blocking our view, or something fundamental about the bursts themselves. One possibility lies in the limitations of our telescopes. Lower frequency radio waves are notoriously tricky to capture. They're easily drowned out by Earth's own radio noise, from lightning storms to cell towers. Even the ionosphere, the layer of charged particles encircling our planet, acts like a frosted window, scattering and absorbing these long wavelengths before they ever reach the ground. Space-based observatories could bypass this interference, but so far, most FRB hunters are Earth-bound, their views partially obscured by the very atmosphere that protects us. But the plot thickens. Some telescopes are sensitive to low frequencies, like the low-frequency array LOFAR in Europe, which scans the skies down to 10 MHz. If the lack of low-frequency FRBs were purely an observational hurdle, LOFAR should have spotted at least a few by now. Instead, its detections remain stubbornly sparse, suggesting something else is at play. This scarcity hints at an intrinsic cutoff, a point below which FRBs simply don't emit much energy. Imagine a piano where the lowest keys don't produce sound, not because they're broken, but because the instrument wasn't built to play them. Then there's the cosmic filter theory. Intergalactic space isn't perfectly empty. It's filled with a diffuse plasma that absorbs and scatters low-frequency radio waves more aggressively than higher ones. This phenomenon, known as free absorption, could act like a celestial sieve, catching the longest wavelengths before they reach us. The farther a burst travels, the more severe this filtering becomes, which might explain why even relatively nearby FRBs seem to vanish below 400 MHz. It's akin to how red light penetrates fog better than blue, except here, the fog is the universe itself, and the disappearing light is a missing chunk of the radio spectrum. Yet the most intriguing possibility is that FRB sources themselves can't produce low-frequency waves efficiently. Magnetars, for instance, emit radiation through processes tied to their extreme magnetic fields so strong, they might naturally suppress wavelengths below a certain threshold. Picture a guitar string held too tightly. It can't vibrate slowly enough to produce deep notes. Similarly, if the physics governing FRBs favors rapid, high-frequency oscillations, the energy might simply never manifest at longer wavelengths. The absence of low-frequency bursts isn't just a technical curiosity, it's a clue. If future telescopes, like the Square Kilometre Array's low-frequency component, confirm this cutoff, it could help narrow the list of viable FRB engines. Alternatively, if they start catching bursts below 400 MHz, it might upend our understanding of how these cosmic signals are born. For now, the silence at the low end of the spectrum remains one of FRB's quietest mysteries, a gap in the noise that speaks volumes about what we still don't know. The connection between fast radio bursts and magnetars gains startling clarity when we examine another cosmic phenomenon, soft gamma repeaters or SGR. These enigmatic objects behave like magnetars cranked to 11, unleashing sporadic bursts of gamma and X-rays that can outshine entire galaxies for milliseconds. What makes SGRs so compelling is their eerie resemblance to FRBs, not just in their sudden, violent outbursts, but in the underlying physics that might link these seemingly disparate events. Take SGR 1935 plus 215, the same Milky Way magnetar caught producing FRB 200428. For years before its radio burst, this object was known primarily for its gamma-ray flares, brief, unpredictable eruptions caused by starquakes in its crust. These quakes occur when the neutron star's unimaginably strong magnetic field stresses its surface to the breaking point, fracturing the rigid outer layers like glass under pressure. Each fracture releases pent-up energy, accelerating particles to near light speed and generating intense electromagnetic outbursts. Sound familiar? It should. This process mirrors what many theorists believe powers at least some FRBs, just tuned to a different frequency. The parallels run deeper. Like repeating FRBs, SGRs exhibit erratic burst patterns, with flares ranging from milliseconds to seconds in duration. Some, like SGR 1806-20, have even produced giant flares, super-energetic events prefaced by weaker precursors, not unlike how some FRB repeaters build up to their most intense bursts. The key difference lies in the energy spectrum. SGRs dominate in high-energy gamma rays, while FRBs blaze in radio waves. yet this might simply reflect different facets of the same underlying mechanism. Picture a lightning bolt seen from one angle. It's a dazzling optical flash captured by radio antennas. It's a crackle of static. Similarly, magnetar outbursts could manifest as gamma rays when we observe their high-energy cores, and as FRBs when we catch their particle jets edge-on. This duality gained traction in 2020 when astronomers witnessed SGR 1935 plus 215 emit both an X-ray burst and an FRB within seconds of each other. It was the Rosetta Stone moment. Theorists had hoped for direct proof that a single object could produce both phenomena. The X-rays likely came from the starquake itself, while the FRB may have been generated by shock waves racing through the magnetar's twisted magnetic field, accelerating electrons into coherent radio emission. This 2-for-1 outburst suggests that FRBs and SGR bursts aren't just cousins. They might be different expressions of the same magnetar tantrum, separated only by the viewing angle and local plasma conditions. But here's the catch: not all FRBs have observed high-energy counterparts, just as not all SGRs produce detectable radio bursts. This discrepancy hints at a critical variable, perhaps magnetic field geometry, plasma density, or the severity of the crustal rupture. Some magnetars might choose to channel their energy primarily into gamma rays, others into radio waves, depending on how their environment filters the outburst. It's as if the universe handed magnetars a menu of ways to explode, and each one orders differently. The FRB-SGR link also helps explain one of fast radio bursts' biggest mysteries: their staggering energy output. Giant flares from SGRs can release up to 10 to the 46 ergs in gamma rays, dwarfing even the most powerful FRBs. If just a fraction of that energy were diverted into coherent radio emission, it could easily account for extragalactic FRB intensities. This rescues theorists from having to invent entirely new physics to explain FRBs. Instead, they can adapt models already developed for SGRs with minor tweaks for radio efficiency. Yet the most tantalizing implication is time. SGRs often show activity cycles, periods of frequent bursts followed by years of quiet. If FRBs follow similar rules, it could explain why so many appear to be one-offs. We might be catching them in fleeting windows of hyperactivity, with long dormant phases in between. This would make the hunt for FRB progenitors even trickier, as their birthplaces could appear completely normal when not erupting. The growing kinship between FRBs and SGRs doesn't solve every puzzle. Some FRBs still resist magnetar explanations, and not all SGRs have been caught producing radio bursts. But it does offer a roadmap guiding astronomers toward a unified theory of neutron star outbursts. Whether through starquakes, magnetic reconnection, or relativistic shocks, these extreme objects are teaching us that the universe's most violent whispers and loudest screams might just be different verses of the same cosmic song. Imagine trying to hear a whisper in a crowded stadium. That's the daily struggle astronomers face when hunting for fast radio bursts. Earth's atmosphere is a cacophony of radio noise, from lightning crackling across continents to satellites beaming data through the void. Even mundane human activity adds to the chaos. Microwave ovens, Wi-Fi routers, and cell towers all flood the airwaves with interference that can masquerade as cosmic signals. In 2015, researchers at the Parkes Observatory in Australia were baffled by mysterious bursts they dubbed puritans, only to later trace them to staff reheating lunches during observations. The universe's most energetic radio bursts often arrive disguised as terrestrial static, forcing scientists to play an endless game of cosmic whack-a-mole. The interference problem isn't just about volume, it's about precision. Modern radio telescopes like CHIME and ASCAP scan thousands of frequencies simultaneously, creating torrents of data where genuine FRBs might appear as faint ripples in an ocean of noise. Satellites pose a unique challenge, their transmissions drifting across the sky with orbits that can mirror distant celestial motions. SpaceX's Starlink constellation alone beams thousands of signals Earthward, each a potential false positive. Compounding the issue, many FRBs share traits with human-made radio pulses, narrow bandwidths, sharp durations making them nearly indistinguishable from radar pings or aircraft telemetry without painstaking analysis. To sift signal from noise, astronomers employ clever technological fixes. Machine learning algorithms now scour telescope data in real time, trained to recognize the subtle chirp of an FRB's dispersion, a frequency sweep caused by intergalactic electrons that artificial signals lack. At the Canadian Hydrogen Intensity Mapping Experiment CHIME, custom hardware called the Real-Time FRB Engine processes 8 terabits per second, flagging potential bursts within milliseconds. Even geography helps. Telescopes built in remote locations like the South Pole or Greenland's ice sheets leverage natural radio quiet zones where frigid emptiness dampens human interference. The next frontier involves space-based detection. Projects like the proposed Farside Lunar Radio Telescope aim to bypass Earth's noisy atmosphere entirely, planting antennas on the Moon's far side, a pristine shield against our planet's radio clamor. Until then, every new FRB captured is a testament to both cosmic violence and human ingenuity, a whisper plucked from the static by minds determined to hear the universe's faintest screams. What if we could use fast radio bursts as cosmic flashlights, illuminating not just their mysterious origins, but the very structure of space-time itself? This is the bold promise of FRB cosmology, a vision where these fleeting signals become precision tools to map the universe's hidden architecture. Every burst that races toward Earth carries encrypted information about the vast intergalactic highways it traverses, from the diffuse plasma between galaxies to the gravitational warping of dark matter. Unlike traditional telescopes that capture light from stars and galaxies, FRBs pierce through the cosmic fog, revealing what lies in the shadows. Here's how it works. When an FRB travels across the universe, its radio waves interact with free electrons in the ionized gas strewn between galaxies. This interaction produces a telltale delay, a dispersion measure, that literally counts the number of electrons along the burst's path. The more stretched out the signal, the denser the material it's passed through. Imagine pouring water through different grades of sand. The time it takes to seep through reveals the sand's density. Similarly, each FRB's dispersion provides a direct measurement of the otherwise invisible matter threading the cosmos. Already, bursts like FRB 180924 have traced the faint tendrils of the cosmic web, confirming theories about how galaxies cluster along vast, interconnected filaments. But the real revolution lies in the future. With thousands of localized FRBs, astronomers could construct a three-dimensional tomographic map of the universe's matter distribution, a project dubbed cosmic cartography. Unlike traditional methods that rely on the light emitted by galaxies, which can be biased toward bright, star-forming regions, FRBs sample every electron in their path, offering an unbiased inventory of cosmic structure. This could settle raging debates about the missing baryon problem, the decades-old mystery of where half the universe's ordinary matter has been hiding. Early evidence suggests it's been lurking in warm, hot intergalactic plasma, a diffuse soup too faint to see but thick enough to slow FRB radio waves. Even more tantalizing is the potential to probe dark energy, the enigmatic force accelerating the universe's expansion. By tracking how dispersion measures change with distance, astronomers could test whether dark energy's strength has varied over cosmic time. Some models predict that FRBs from different cosmological epochs should show subtle deviations in their dispersion, fingerprints of dark energy's evolving influence. It's like measuring the stretching of a rubber band over billions of years to deduce the properties of the hand pulling it apart. The upcoming square-kilometer array, set to detect millions of FRBs, could turn this vision into reality. Paired with optical surveys like the Vera-Rubin Observatory, it will match bursts to their host galaxies, creating a multi-messenger map of unprecedented detail. We might uncover voids where matter is inexplicably scarce, or filaments denser than simulations predict anomalies that could hint at new physics. In this grand experiment, every FRB is both a message and a measuring stick, a fleeting signal that unveils the universe's scaffolding. The same bursts that once baffled astronomers could become our most powerful tools for decoding cosmic evolution, transforming whispers from the dark into a blueprint of everything. Not every cosmic whisper comes with the roar of a full-fledged fast radio burst. Over the past few years, radio telescopes have begun picking up something unexpected, fleeting blips of energy so faint and brief, they barely register above the static. These marginal signals, nicknamed baby FRBs, last mere microseconds and pack a fraction of the punch of their more famous cousins. Yet their very existence raises a provocative question. Are we catching glimpses of an entirely new cosmic phenomenon, or simply seeing the infancy of what could one day become titanic bursts? Take the case of FRB 190607b, detected in 2019. Unlike the blazing millisecond flashes of classic FRBs, this signal fizzled out in under 30 microseconds, faster than the blink of an eye. Its energy output was equally unimpressive, barely a thousandth of a typical FRB's might. At first, astronomers dismissed it as terrestrial interference, another blip in the endless noise of Earth's radio cacophony. But then came more detections, each with the same peculiar fingerprint: ultra-short durations, narrow frequency ranges, and dispersion measures suggesting extragalactic origins. These weren't glitches, they were something else entirely. One theory suggests baby FRBs could be the misfires of cosmic engines not quite powerful enough to produce full bursts. Picture a magnetar's crust beginning to fracture under magnetic strain, only for the quake to fizzle before releasing its full fury, a cosmic sparkler sputtering out before it can ignite. Alternatively, they might stem from entirely different progenitors, like the collisions of microscopic black holes or the evaporation of primordial cosmic strings. Their brevity hints at emission regions far smaller than those powering standard FRBs, perhaps no larger than a city block in scale. What makes these marginal detections so tantalizing is their potential to rewrite the rulebook. If baby FRBs operate under different physics than their more energetic counterparts, they could represent a missing link between FRBs and other transient radio phenomena. Some researchers speculate they might even outnumber traditional bursts by orders of magnitude, an unseen population of cosmic fireflies flickering faintly in the dark. The challenge lies in catching them. Current telescopes optimized for millisecond-scale bursts often miss microsecond flashes entirely, leaving us blind to what could be the universe's most common and least understood radio whispers. Future observatories like the Square Kilometre Array promise to change that. With unprecedented sensitivity to ultrafast radio pulses, they could reveal whether baby FRBs are cosmic dead ends or the first murmurs of something far grander. For now, these enigmatic signals linger at the edge of detection, a reminder that even in the study of the universe's loudest explosions, the quietest voices might hold the most surprising secrets. Fast radio bursts have rewritten the cosmic rulebook since their discovery, yet the more we learn, the clearer it becomes we've barely scratched the surface. The biggest unanswered questions loom like shadows at the edge of our understanding, each one a doorway to deeper mysteries. At the forefront, what cosmic furnace generates these staggering bursts of energy? Magnetars remain the prime suspect, but their confirmed emissions, like the Milky Way's FRB 200428, fall thousands of times short of the most powerful extragalactic bursts. Could younger, more volatile magnetars in chaotic stellar nurseries bridge this gap? Or are we missing something fundamental, like unseen particle interactions or exotic physics amplifying their power? The puzzle deepens when you consider the outliers bursts so energetic, they strain the limits of known astrophysics, demanding engines we haven't even imagined yet. Then there's the enigma of repetition. Why do some sources, like the infamous FRB 121102, fire off dozens of bursts in erratic patterns, while others vanish after a single brilliant flash? The divide isn't arbitrary. Repeaters tend to cluster in star-forming galaxies, their bursts weaker but persistent, while one-offs often emerge from calmer galactic neighborhoods with apocalyptic force. This dichotomy hints at two distinct cosmic engines, one capable of recurring tantrums, the other doomed to self-destruct in a cataclysmic finale. But even this neat classification crumbles when faced with exceptions, like the rare repeater that occasionally unleashes a monster burst, blurring the line between the two camps. Are we seeing different phases of the same phenomenon, or entirely separate species of cosmic flare? Perhaps the most tantalizing question is whether we've even found all the varieties that exist. Marginal signals like baby FRBs, microsecond whispers 1,000 times fainter than their full-grown counterparts, suggest an entire hidden population lurking beneath our detection thresholds. Could there be ultra-long FRBs stretching for seconds instead of milliseconds, or bursts entangled with gravitational waves, their radio flashes paired with ripples in space-time? The universe has a habit of surprising us. Every time we think we've mapped the boundaries of what's possible, it tosses another anomaly into the mix. Future research holds the keys to these puzzles. Next-generation telescopes like the Square Kilometre Array will scan the skies with unprecedented sensitivity, catching thousands more bursts and pinpointing their origins with surgical precision. Meanwhile, multi-messenger astronomy, linking FRBs to gravitational waves, neutrinos, or high-energy photons, could reveal hidden connections between these signals and other cosmic cataclysms. Somewhere in this flood of data, patterns will emerge, anomalies will sharpen into focus, and the pieces of this celestial jigsaw will start falling into place. The beauty of these mysteries lies not just in their complexity, but in what they reveal about our place in the cosmos. Each unanswered question is a reminder that the universe is grander, stranger, and more inventive than we've dared to dream. Fast radio bursts aren't just cosmic oddities, they're invitations to venture beyond the edges of our knowledge, into the uncharted territories where the next great discoveries await. Fast radio bursts have taken us on a journey through 30 of the cosmos' most tantalizing puzzles, from their mind-bending origins in magnetars and cosmic collisions to the bizarre patterns that hint at unseen physics. We've explored how these fleeting signals map the universe's hidden matter, how they might whisper secrets about dark energy, and even how they flirt with the boundaries between natural phenomena and something more intentional. Yet with each answer, new questions erupt like sparks from a cosmic fire. Why do some bursts repeat while others vanish without a trace? What lurks behind the hostless bursts that seem to come from nowhere? And could these flashes truly be the echoes of action stars collapsing or cosmic strings vibrating through space-time? What makes FRBs so extraordinary isn't just their energy or their distance, it's how they embody science's most thrilling frontier, the unknown. They remind us that the universe is stranger, wilder, and more inventive than we've yet imagined. And the hunt is far from over. Telescopes like the Square Kilometre Array, set to come online in the coming years, will detect tens of thousands more bursts, peeling back layers of mystery with unprecedented precision. These instruments won't just solve puzzles, they'll undoubtedly unveil enigmas we haven't even thought to question yet. So stay curious. The next great cosmic revelation might be hiding in a burst we detect tomorrow, or in the data we're sifting through today. Which of these 30 mysteries fascinates you the most? Is it the eerie repetition of FRB 121102, the staggering energy of one-off blasts, or the possibility that some bursts could reshape our understanding of dark matter? Drop your thoughts in the comments because the story of fast radio bursts isn't just unfolding in observatories and research papers. It's a conversation, a collective quest to decode the universe's most electrifying signals. And who knows, the next big clue might come from a fresh perspective, a wild idea, or even a viewer like you. After all, the cosmos loves a good plot twist.